Hello, everyone. So we're here today to introduce you to our project, which is optical characteristics of security inks. So first, let's start with some context about inks. There are many different types of inks, and of course, security inks used, for example, in your identity papers and money, for example, are different from regular printing inks, such as offset inks, in order to make counterfeiting more difficult. Those non-standard inks possess different properties, which depends on various factors, such as the thickness of the deposit, the pigment concentration, or the particle distribution, which makes it quite difficult to reproduce even from batch to batch without a suited method. Reproducibility is very important because a tiny error can easily distort the final result. For instance, when stacking multiple layers of inks. And to develop a suited method, we first need to characterize those inks in order to compare them. Which brings us to our problem. How can we characterize those inks? And how can we measure if batches of supposedly the same ink possess similar properties in order to get an idea of their reproducibility? For that, our objective is to obtain the spectral absorption coefficient K and spectral scattering coefficient S, which basically quantify how much a medium absorbs and diffuses light. To calculate that, we tried several first on inks, and when we had a plausible and convincing result, we applied the method to the security inks. For the measurement, we used an X-ray spectrophotometer, which allowed us to obtain the reflectance and transmittance factor of the inks.
So we used the Kubelka-Munk model, which is the main model for light scattering, and add a Solderson correction, which adds precision by taking into account the reflection at the layers interfaces. So here, these are the equations that we used to go from our measurement of R and T to K and S. We adapted those equations with suitable values to describe the medium, and it gave us S and K. Actually, it gave us S times the thickness and K times the thickness, and we just measured the thickness with a micrometer. We had three colors: cyan, magenta, and yellow, that were divided in 4 batches, and each batches were divided in 2 samplers. So we have to do about 260 measurements. So there you can see the result it gave us for the magenta batches. As you can see, there is a slight variation into the K coefficient. And we see that the inks are strongly absorbing and very less diffusing compared on the scale. So that explains the very colored and transparent aspect of the inks. However, we also encountered some difficulties in the process, for example, with the cyan batches. As you can see, there are more disparate, and it may be due to the slight variation into the concentrations of ink. So it's amplified by the fact that they are strongly absorbing. Moreover, we noticed a difference between the measurements, whether we measure with ink first or the film first. because the ink is deposited on the surfaces and not inside. So all in all, we did observe that perfect reproducibility is quite difficult to obtain regarding to the S and K coefficients. Currently, we have measured that the relative delta maximum between batches is at around 6%. And to go further, we could focus on a better adaptation of those equations to guarantee a good reproducibility from batches to batches. And we could maybe develop a method using reflectance spectrophotometer to quantify the gradient and the particle distribution. Thanks for listening.